Yeah, thank you very much for the nice invitation for the conference, also for introducing me. I will talk about a recent work together with two of my PhD students, Maren Klever and Tim Wertmann, and my former PhD student, Christian Löbert, who's now working in industry, earning a lot of money. So he's more or less out of science. So the focus is actually on one component of the multigrid method, how to do this in low-rank formats. And on the way to get there, I will explain the model problem and a few technical details, but I want to focus exactly on one little aspect, that's the smoother in the multigrid method. Okay, so the PDE model problem should not be a difficult problem. It's actually a nice toy problem in mathematics. Because then I can introduce standard multigrid method and explain very, very briefly what is used in the multigrid method, what are the components, what we need. What we want to have is easy to say. We want to have a convergence guarantee. So we want to converge to the solution. Let's say it's a linear system, which has a unique solution. We want to converge to the solution. And but there's a little catch to that, because it's in high dimension, so we need a special tensor format, and that's in this case the hierarchical Tucker format. But actually in my presentation, it doesn't really matter that it's the hierarchical Tucker format. It could be matrix product states. It could be any format in which you have some sort of truncation, so you can produce quasi-best low-rank approximations. So it could be in the Tucker format, like in the previous talk, or a variance of that. For example, this subdivision hierarchical format from the previous talk is perfectly viable. And then at the very end, I will come to the critical, no, it's not the critical, but the nice component in the multigrid method that we can analyze, and which was already known for matrix equations, and this is now also possible in the HT and the hierarchical Tucker format, and that's the Jacobi smoother depending on parameters. So that's the whole story. Multigrid is easy, Jacobi smoother is easy, but we have high-dimensional parametric dependency. Okay, so first I have to mention that part of this work was supported in all these nice programs in Germany, and it's all areas, computer science, engineering, physics, all of them involved. And the model problem is a well-known one, everyone knows this. There's a particular emphasis. So it's an easy toy model problem in low dimension. So you should think of the spatial dimension, X. I always use this numerical analysis notation. So omega is the physical domain. It's not something random. So it's just a two-dimensional simple unit square, unit cube or something. So X is, you could say, the lame variable. And I take the Laplacian or this diffusion problem with the diffusion coefficient A depending on the spatial variable X. But then in addition, there is a parametric dependency on P. Could be on the right-hand side, that would be more or less easy, but in particular of interest is this diffusion coefficient A depending on parameters P. Okay, so I want to simplify a little bit, not very much, just a little bit. So now I take P as a discrete variable, so it's just has D components, and each of the components ij is from capital Ij, a discrete set, let's say of nj possible values. So that's actually quite easy. So everything is already discrete. If you think of P a random variable and A a random field, then you would first have to find such a nice approximation. This is already done. So let's think of an engineering application where you have a finite number of parameters that you want to tune. And then what we first do, that's the easy step, it's discretization with respect to the spatial variable X. So this is your usual finite element or finite difference discretization, but you could use finite volumes or I don't know, whatever you like. So you end up with since this is a linear operator, in U, in the unknown solution, you end up with a linear system. I just reuse the variables. So on top, I have the continuous function U, and here for the discrete vector, I use just the same variable U. Now, everything depends on the parameter P. So on the right-hand side, this is maybe not that critical, but in the operator A, I have a parametric dependency on P. Now, the typical situation, which we will focus here, is an affine parameter dependence. And this is slightly misleading because it just, as it's written down in the formula, so you have the constant part A naught, then you have coefficients depending only on one of these variables, on one of these indices at a time, and a summation over those. So it's affine in this product with a matrix AJ. Okay, of course, in the typical finite element discretization, A naught and AJ, they are all sparse. So they are typically very huge, but sparse, but not astronomically huge. So these are still matrices you could handle, like, I don't know, 1,000,000 times 1,000,000 of size. And the parameters, the IJ, of course, if D grows, this will be incredibly many. So it's all possible combinations cannot be stored. So you cannot form this A of P for all possible values of P. You can only form these matrices A naught and AJ, and then have here this parametric dependency. So if you write down the operator, it's perfect. It's already nicely represented and compressed. You're done. So the problem is you want to invert the operator depending on the parameter P. And then what is not done in this talk, there's a straightforward, more or less trivial preconditioner or an approximate solver that you can use and then start a linear iteration. And that is just taking the constant part, for example, or the average. Okay, there's a question. The sigma is really just, in this case, a scaling function. So let's say a real valued scaling function. So it's one-dimensional. I could also write down an explicit formula if I have a certain representation in mind. So the sigma j are known. I don't have to assume much, but of course they have to be scalars. If these were matrices, okay, it's still possible, but I don't want to do this here in this talk. So it's the critical part is that each of these summons depends only on one, or let's say a very small number of these variables. So here it's just one index j going from 1 to d. Okay, so this is my model problem. So this is my matrix depending on the parameters. The P just concatenates all the I1 to ID. This is the equation I want to solve. And I'm interested in this full map. So going from the parameters to the solution. I have written down the solution U in terms of inversion times the inverse operator times the right-hand side. And you should think of this as being a pre-computation step. So if I could get this whole map, then I have essentially a table of all solutions. So I can just quickly pick one solution for one parameter combination. I don't have to recompute anything. So this is the same situation as in model reduction. But in model reduction, you say in the offline phase, you do some expensive computations. And in the online phase, you have a very quick solution map because you have this very, very reduced model. In our case, it's more like a table, like a logarithm table. You just read out the logarithm and that's it.
There's a question of Joseph Landsberg. Is sigma a scalar or a matrix value?
Ah, yes, that was already on the previous slide. That's the sigma j are just scalar functions. For simplicity, you can extend this, but that's not important for the moment. Just assume it's a scalar function. So the A naught and AJ are discretizations on your finite element space. So this is, I don't know, 1,000,000 times 1,000,000 matrices, A naught and AJ. And these are just scalar functions. Okay, so what I will not talk about is whether or not this mapping from the parameters to the solution, so my interesting map, admits a low rank representation. It's of course an important and very interesting question, but very difficult, and we will not answer this here. And just not to confuse anything, I'm not talking about a high dimensional spatial dependency. Then Let's assume A is just identity, constant 1, let's say. Then this is a simple question. So this is already answered. But in our case, X is from a lower dimensional space, and there you have the parametric dependency, which gives the problems. And mapping the parameters to the solution, so that's not completely trivial how to prove that there is a low rank representation. Okay, now next little toy example. Here you can see the scaling functions, sigma 1, sigma 2, sigma 3, depending on the parameter, discrete parameter I1, I2, I3. And I write down the operator in this form, depending on the choice of these three parameters. And you can write this down in separable form because you have the summation, and you can write it down such that each summand is just a product of entities. You can see the product structure here, you can see the product structure here, and in the third part, and you can write this down just as a concatenation as outer products of these vectors. And then you end up with something which is here in this picture 4-dimensional, because you have 3 dimensions for the 3 parameters and 1 dimension just for the spatial variable. Whether this is 2, 3 or something dimensional, it doesn't matter. I just say, okay, it's 1 variable. Now this is very simple. You don't need any special tensor formats because you have this formula on top. So there is no special tensor structure needed, but it fits into essentially every tensor structure. You can just represent it in any form you like. Okay, so how do you want to solve such a problem? Now, for just a moment, now on the left-hand side, you see this parametric dependency. That's the colored ones, the 3 colored ones on the left-hand side. And you have the spatial dependency, that's the dark gray block on the lower right-hand side. Now, for a moment, just assume that the parameter P is fixed. So there is no parametric dependency, and I have to solve. So usually in talks about tensors, you just say, I have some solver. But in my case, this is important. So for a fixed parameter, think of this cookie problem on top. So you have 9 of these areas where you have diffusion coefficients that are different from the background diffusion coefficient, let's say from the A node. You have 9 of these coefficients, but they are fixed, just some values. Maybe there's a smooth transition from the background 1 to this diffusion coefficient. And now you have to solve this problem, but just this plain problem for 1 parameter combination. And in order to do this, we use a multigrid hierarchy. So you have discretization on different levels. And that's the only thing I want to explain. On each of these levels, you can nicely represent certain frequencies. So high frequencies on the finest grid, medium frequencies on the medium grid, and very low frequencies on the lowest grid. Okay, why do we split into these frequencies? It's a subspace decomposition, and on each of these spaces, only considering the high frequencies here, or only considering the low frequencies here, we do have nice solvers. It's a nice frequency decomposition. That's the idea of the multigrid method. Solve for each layer of frequencies on each of these grids. On the coarsest grid, let's assume it's simple, not completely simple, but just assume you can solve on the coarsest grid, and then you just have to do something on these other grids, and that's not solving the whole problem, just solving for a certain frequency band, and that's called the smoother. It's sometimes Richardson, sometimes Jacobi, and I will note this later on. Then you need a transfer between these grids, the prolongation restriction, so just interpolating functions on the next finer grid and the adjoint to go down. So they are straightforward. It's not of interest in this talk. What we're interested in is this: how do you solve for certain frequencies on one level? And what I also don't want to talk about in detail is that we don't care about this truncation or approximating tensors in low rank format. I assume this is given. So we have the hierarchical singular value decomposition, and we have seen this in the previous talk. Yes, there is a singular value decomposition available. It was also in the first talk by Markus, and this is now given. So what I want to focus on is the smoother. And I have to tell you how this, what is this smoother? How does it look like? And I also have to introduce a little bit about this tensor format. To give you a little preview, be careful. On the y-axis, you see the accuracy, and I measure now the residual, but just the L2 residual of the solution. It's a bit stupid. I shouldn't do this, but I do this because it's easy. It's just the L2 residual, discrete L2, the same in this case as the continuous L2 residual of the solution. And you can quickly see, okay, this converges nicely. But on the x-axis, you have a logarithmic scale. That means the Jacobi method that you see on top here, it's a plain stupid solver, no hierarchy involved. It's very, very slow and needs many thousands of steps. If you introduce slightly better multigrid hierarchy with a Richardson smoother, it's already good. But because we have these parameters that could be sometimes constant, sometimes non-constant, the Richardson smoother is not very good. It's already okay, but if you go to fine grids and high contrast, this will use a lot of steps. But the Jacobi smoother seems to be just what you want. So it's really order one, I don't know, 6 steps, and you have the solution. Now, how does it work? What is the Jacobi smoother? And that's written down here. You just, on the right-hand side, you can see essentially the residual, the defect. And here you have an iteration. The U, the index L, indicates my iteration index. So it's just going from one iteration, from one approximation to the next, getting a better and better approximations. And that's what you can see here, the convergence rate, fantastic. All you have to do on one level of the grid is inverting the diagonal of the matrix, which is of course trivial because it's only a diagonal matrix. How complicated could it be? It is complicated because you have the parametric dependency on P, and we have to cast this into our tensor format. So just inverting each of the diagonal entries, those are astronomically many, not possible. We need a nice formula for this inverse of the diagonal. And that's what I'm talking about. So the multigrid method, just believe me, we have a straightforward convergence proof if we have the smoothing property of this Jacobi smoother. And the smoothing property we have already from the standard multigrid theory for the Jacobi smoother. The only thing that changes here is the parametric dependency. And if I can find an approximation to this inverted diagonal of any accuracy that I like, I do have the convergence guarantee of the multigrid method. Okay, it's different from alternating least squares and so on. Now, the only problem is to cast this into low-rank tensor format. And the tensor format, there's no need to introduce too much. It's a separation of variables. If you have 2 indices, I1, I2, you separate it into left and right factor. And you can do this with many factors. That's the CP format, but that has technical problems, I would say, to compute with those. Now comes the idea of Hackbush. You just separate into groups of variables. So let's say you have 4 variables, 4 parameters. You group the first 2 and the second 2 together, do this first separation, and then continue with the left and the right factor and separate here I3, I4, and on the left-hand side I1, I2. So I write down this in formulas, but you don't have to look at the details of these formulas. It's just a recursive singular value decomposition, you might say. Or, as in the previous talk, a recursive rank revealing QR, or whatever you want to use in order to find a separable representation with as few terms as necessary. Okay, now I give you just one of these separation steps because then it's a straightforward recursion, and this is what we call the nestedness. It's just a recursive singular value decomposition. And because it's based on the standard matrix singular value decomposition, you inherit all the nice properties of the matrix singular value decomposition. For example, tensors of rank bounded are closed. And of course, we do have something like a singular value decomposition available. So this is what it looks like. And you've seen this picture in the very beginning of the talk. So here we have the different variables, let's say 3 parameters at the spatial variable, and we just agglomerate them by forming outer products of these. Now, in order to store everything, you just have to store these tiny matrices, these tiny cubes. And it's the same structure in higher dimension. So you just add more of these tiny cubes. Or you can do this in a linear fashion. And that's what you know from roughly from matrix product states or tensor trains. It's roughly the same structure. And in my talk, it doesn't really matter what kind of structure you use, matrix product states or hierarchical tensors, hierarchical Tucker or Tucker, all of them work nicely. What we need is a truncation procedure. And that has to be efficient in the number of entries or the number of the size of the storage for the tensor. And that depends linearly in the dimension. Of course, that was also mentioned in the previous talks. You have a cubic dependency on the rank. So you have to be careful. You want to keep the rank low at all times. Okay, so now comes a lot of vast literature, but not on specific details on the multigrid algorithm, but on tensor approximation representation in general. Okay, what we basically need is, once we form the summation of two tensors and the rank will formally increase, we have to truncate back down to smaller rank. So we have to find an approximation up to any prescribed accuracy or prescribed rank. Typically, what we want to have is a prescribed accuracy bound and then adaptively find this approximation U tilde. But that's given in this talk. We do have a procedure that can do this. And you just get this extra factor. We've seen this in previous talk as well. So there appears an extra factor of d or square root of d, but that is not critical in this case. So typically we don't see such a huge factor here. And even if we do, that's not so important. So whether this is 10 to the minus 5 or 10 to the minus 6 in total, it doesn't matter. So a factor of 10 here is not really relevant for us. Okay, now we come back to the main problem. You can already see we're very close to the very last slide. And that's the interesting part of the talk. So it's like a meta talk, an idea how we can solve the problem by solving a different problem. Now, this is my basic problem. I have an operator A of P, depending on this parameter P. It could be this affine dependence, which will be nice in this case, but you can also try to generalize this. Now, how do you find and how do you prove that you can find an approximation to the inverse of the diagonal depending on all these parameters? So you have to compute the diagonal of this operator to the minus 1. And now we look at one entry on the diagonal. So we take, since this is linear or affine, we just take the indices QQ, the diagonal indices of each of these matrices, and I just abbreviate. Little a naught is now a scalar value. I have a summation over little aj, which is also a scalar, just the entry on the diagonal. And then now this coefficient sigma, and now here's the important part. This depends on the parameter ij. Okay, if you have a summation of these parameters and take the inverse, you have a full coupling, but you can write down, if you have the correct sign in this case, let's say z is positive, you can write down the inverse in terms of exponentials. So everyone knows that these exponential functions are the right thing. You use them everywhere, and it's the same here. But we have an explicit separation because it's one-dimensional. We have explicit formulas for these omegas and the alphas. Now I insert this approximation here for computing the inverse. And then I can write down these entries because I insert the summation in the exponential, function. I get a product form, and that means now everything is separable. So independent of the tensor formats, you always get the separable representation. It fits into everything. Now, since we have an explicit formula for the omega and the alpha, the AJs are the given entries here, we have an explicit formula for the approximate inverse of the diagonal. And this can now be inserted into my tensor format. So you can see this nice form here. It's in the CP format, and then you can transfer it to the HT, to the TT, matrix product states, or whatever you like. So you can find an approximation very close to the true Jacobi smoother in the tensor format. Once you have this, you don't have to actually care about the tensor format for the operator because you have a solver where you can write down all the components in this nice separable form. What you cannot do, you have to actually form the iterates, the UJ. Please be careful. I will go back a few slides. Don't be confused.
So Lars, you have 5 minutes left.
Yeah, I'm already close to
I
the
see.
finish line. I have to find the slide with UJ. Here. So this is my iteration where I go from one of these solutions to the next one. And this, of course, has to be represented in my low-rank tensor format. And after doing these summations, I have to cast this back to smaller rank in my low-rank tensor format. So there I need the truncation, there I need the tensor format, and there I need to know something about the true solution or the mapping from the parameter to the solution. But I don't need this here for the Jacobi smoother. There I can prove it. Okay, so that was what you're doing. It's very easy and simple, and you can prove it. And of course, we have a reference at the very end where you can read up everything. So this is the easy part. So you can form the inverse of the diagonal, even if it's depending on all those parameters. You can prove convergence. That means uniformly in all of the parameters. And of course, you have numerical tests that confirm this. Now, the open questions, the difficult ones is, where do you go from here? How do you generalize this? Because the multigrid method is a nice framework, and then you have lots of extensions on how to use it. For example, you want to have more proficient, more elegant smoothers. So the Jacobi is a simple one, but maybe you want to do something, I don't know, in the direction of convection-dominated problems. So you want to change the smoother, which is not completely trivial. You also want to go to in the direction of algebraic multigrid methods. And there's a particular reason for that. I don't want to go into this because maybe you don't know what I mean by algebraic. In particular, there's an interesting part, and that's what I explained to you. If you prolong, you just do an interpolation. If you want to restrict, you take the adjoint, which is a good idea, but not if you have if your problem is not very close to the simple Poisson problem. So in our case, these parameters might introduce something that you have to catch with a prolongation and restriction. And that is what we're working on. And the last part is when you go from a finer to a coarser grid, you do not change anything in these parameters and the dimensionality. So the problem on every level is roundabout of the same complexity, which is not so nice in the multigrid method. And therefore the question was, can you reduce dimensionality when going to coarser grids, which would be perfect. And you end up hopefully with a one-dimensional problem on the coarsest grid, and you can directly solve it without any tensor structure. But that's still an open question. So at the very end, I want to point you to the corresponding article. An archive version is freely available, and it's already accepted for this new journal, Computation and Visualization in Science and Engineering, which is the corresponding journal to the existing one, but this one then has free of charge open access. Okay, you can see also the previous articles leading to this one. And with that, I have just one little tiny reminder at the very bottom. And that is that many of these ideas go back to ideas from matrix equations, because that's the two-dimensional analog to the high-dimensional tensor equations. And there's a corresponding conference, and it's this year in Perugia. And I'm very hopeful and optimistic that in September, we are all vaccinated and can nicely join the conference in person in Italy. And if that's not possible, we will do this online. Okay, with this, I want to thank everyone for listening and the organizers for organizing. Thank you very much.